All right, I want to do a little bit of a recap and review of p-forms, but I want to emphasize the complementary idea of p-vectors, which are mathematically, in all sense of what we've talked about, are identical to p-forms. But what we've already discussed is we've discussed this exterior product space. Let's see if I can make it a little better. The pth exterior power of a vector space. And I've noticed when I went back and reviewed one of my old lectures, I actually wrote this like this in the earlier lectures. The exterior product of the dual space. And because I was talking about p-forms, and p-forms are always going to be wedge products of one forms, right? Omega, delta, lambda, wedge, say, gamma, where there are p of them. P1, and each of these is a one form, which is an element of the dual space. And so I kind of wrote it this way, but that's actually not the correct way to write it. The correct way to write it is this way. And the distinction between p-forms and p-vectors is made by putting the p at the bottom for the same underlying vector space. You see, you always start with this underlying vector space as sort of your anchor. And the fact that the p is a superscript is going to tell us that the exterior power space contains wedge product of one forms. Now I'm going to talk about the fact that we can make a wedge product of vectors, v, w, x, z, where they're p vectors, and each of these things are one vectors, and they're all elements of v. And the way to distinguish that exterior power is by putting the p at the bottom. But the underlying vector space in both cases is still v. It's sort of our anchor. And sometimes there's no parentheses here, so the exterior power would be written like that, say. So when I, in the previous lectures, put in this little dual space star, I was trying to remind myself and everybody that we're talking about forms, and therefore we're talking about wedge products of one forms. But that really isn't the standard notation. The standard notation is like this. For example, tensor product spaces, say the PQ rank tensor product space, right? A tensor product space of rank PQ. We don't say V star V, or we don't say, for example, 0 P V star. We just say T P Q of V, where V is the underlying vector space. And the same thing applies here, really. So that's in a little notational thing I noticed where I don't know quite why I did this back in those other lectures, but I changed in the determinant lecture, I noticed, so, and that was the correct answer. So we want to do it this way. But the point that this brings up, what that it highlights, is what is this object here, right? And this object is exactly the same thing we've been studying, but now instead of constructing the elements of the pth exterior power from one forms, we do it from one vector. So I would say take a vector, well, the vector space will be V. So let's say I have a bunch of vectors in V. V, W, X, let me make them lowercase, X, and Z, like that. So now if I wanted to make a 4 vector. Now notice this word 4 vector, right? That's not the same thing as a 4 vector of special relativity, right? Special relativity has 4 vectors, which are these, which is what encodes the mathematics of momentum and 4 velocity and 4 momentum and energy. All of these things, the energy momentum vector, they're all wrapped up in 4 vectors. But this is now a 4 vector in the form, in the notice of, with the understanding that we're talking about p-vectors, which is an element of an exterior power. Unrelated concept. So, but a 4 vector would now be V, wedge, W, wedge, X, wedge, Z. That would be a simple 4 vector. right? You know, just to get away from this 4 vector, I'm going to actually add Q, so I can make it a 5 vector, and that way we won't make any confusion. So I won't have to worry about the special relativity confusion. And I'm sure nobody listening to this thing is drawing that confusion, but just hearing the word confuses my own little pathetic brain. So I'm going to go with 5 vector. But a 5 vector is still the exact same concept. This is a simple 5 vector because this thing is an element of the 5th exterior power of the vector space V, but it can be expressed in a single term, right? It can be expressed as a single wedge product. You can easily imagine something that would look like V wedge omega W wedge X wedge Z wedge Q plus A wedge B wedge C wedge D wedge E, right? And there's no way to combine them into a single set of, let's see, I need 4 wedges for 5 things, into a single wedge product. If you can, whenever you can do that, whenever you can take a bunch of wedges, a bunch of wedge products that are being summed, and put it and convert and sort of find a basis where they're all a single wedge product, that's called a simple P form or a simple P vector. But so we usually work studying just the simple ones because we know that everything's linear. So if you understand it for the simple ones, you just add it together. And remember, this addition symbol is the addition that's ultimately inherited from the tensor product space 0p of V, right? That addition symbol is inherited by this because this is a subset. This U is a vertical subset, right? This guy here is a subset of this. It's a subspace, a sub-vector space of the tensor product space. And as such, it inherits the tensor product space addition. Okay, so so if we took this guy, right, we could do all the things we did before, right? This is V mu E mu wedge W nu E nu wedge X gamma E gamma wedge Z beta E beta, like that, and you pull it all out and you get V mu W nu, oops, W nu X gamma Z beta, then E mu wedge E nu wedge E gamma wedge E beta, just like that. And the and then the wedge product. This is a member of the basis of this space here of the 5th exterior power of the vector space. And so it's all the same, right? There's nothing different. It's just now the subscripts are down, right? And this guy is still understood to be the wedge product of basis vectors, where each of these basis vectors is an underlying basis for the vector space V, and it can be understood as a mapping, right, that's looking for some sort of member of V star. So these are still, vectors are understood to be mappings, just like covectors are understood to be mappings in this context. And it's the same usual thing from here on out. Everything is the same. And in particular now, if you have a vector space V, we now know that we can create V0 of V, V1 of V, the second exterior power of V, all the way to the n-1th exterior power of V and the nth exterior power of V. But now we can also create the same thing with the exterior powers of the vector space itself, right? n-1 of V and n of V, right? Where n equals the dimensionality of the underlying vector space. Now again, notice here, I'm always using V in the parentheses here because we're always referring to the underlying vector space. And there's only n of them because we know that the nth plus 1 exterior power of V is always empty, right? Because of the way we've already discussed this, but the anti-symmetry forces all of the other ones to be 0. Now notice, remember, there's an infinite number of tensor product spaces, PQ, right? You can make those forever and ever and ever, but there's a limited number of these exterior power spaces. And actually a lot of the interesting facts in physics about the world kind of comes down to the limited amount of exterior power spaces. Again, we haven't discussed why these things are important. I know this is kind of weird. We're discussing just the math, and we haven't really talked about why these things matter. And I think that's just my approach. I'm kind of assuming that you're reading other books and you're running across these concepts, and the other books are explaining why these things are important. And I'm just intending this lesson to help sort of take away the mystery of what these things are. We will talk about why they're important eventually, but it's really important to understand sort of what they are. So we now know that with a vector space V, we get all of these vector spaces for free, all of the infinite number of tensor product spaces for free. And we also remember that we learned that the dimensionality of these guys is predictable, right? The dimensionality of these guys is always n choose p, right? And that's true for both of them. The dimensionality is n choose p. It's the same construction, right? These guys were constructed the same way these were, so these all have the same dimensionality structure as these do. So, and we know that the 0th exterior power is the bin of real numbers that defines the vector space. And when we make this a field, when we talk about fields of forms, just like we talk about tensor fields, then this will actually be the infinite C infinity, the infinitely differentiable functions on the underlying space-time. This is going to be the covector space. This is going to equal the vector space itself, right? The first exterior power. The second exterior power we actually constructed in great detail in one of the previous lectures. The final exterior power, but this one, the final exterior power has the same dimensionality as the 0th exterior power, right? They both have dimension 1. They both have dimension 1. The n minus 1th and the nth and the 1th exterior power both have dimension of v. Whatever the dimension is of the underlying vector space, well, of course, those guys share that dimensionality. Like this, dimension v. I guess I should write dimension v star, but that equals dimension v, right? So both of those share the same dimension. And then it's also true that if I go to n minus 2 of v, these two share the same dimensionality. N minus, wait a minute, why, whoops, I just noticed something. I put these guys up here. That's wrong, they should be down here, n minus 1, and this is n minus 2 of v. So these two share the same dimensionality. So now that is where we kind of left off, and what I've done so far is I've added this branch to everything, because all I've done is reconstructed the same mathematics, but instead of using the dual space, v star, we are building the same exterior algebra mathematics out of v. Okay, so what else as a quick review of what we had done before we go on to something new? So now we'll review the exterior power, or the exterior algebra, sorry. And the exterior algebra we'll look at for this little refresher is the exterior algebra of the Pvectors. Now we know the exterior algebra is a direct sum, right? So because it's a direct sum, it's a massive direct sum, we know it's a vector space, and we established it to be an algebra by giving it the product, the wedge product, as the as the monoid multiplication that turns a vector space into an algebra. And what we remembered was that this construction, this direct sum construction, means that every element, because this is the algebra itself, which is a set, it's set endowed with its vector space properties and its wedge product property, and every member of that set is an ordered, well, it's a tuple, right? And how big a tuple? Well, it's a dimension V tuple. However big the dimension is of the underlying vector space, that's how big this tuple is ultimately going to be. Actually, the tuple in some sense is infinite. It's just every slot after dimension V is 0, right? So the first slot contains an element of the 0th exterior power. I'm going to stop using the V for now. The second one takes an element of the first exterior power. The third takes an element of the second exterior power, all the way to the nth exterior power. And like I said, you can consider this to have n plus 1 all the way to infinity, but all of these will equal 0 because of the fact that they're just unoccupied for when the dimension of V equals n. So these will be, so that's the, so we'll just, so instead of pretending it's infinite, we will cut it off at n. And it's a vector, this is a vector space, so it has its own addition property, and we discovered that addition property was if I took A, B, C, D, and I wanted to add it to E, F, G, H, like that, I just add them slot by slot using the underlying addition property of the vector space to which each slot belongs. And that's the rule for how direct sum spaces are vector spaces. You add these tuples together. See, the member of the vector space is the tuple. The sum rule is defined that the sum of two members of the vector space is going to be the tuple that contains the sum of the individual elements. B plus F, C plus G, right? And then D plus H, like that. And each of these sums here are inherited from each of the individual vector product spaces. By the way, this is called a graded algebra. And it's a very important form of algebra. The graded algebras are really important. And this is probably the easiest and the first example. Well, the easiest example is the polynomials, which actually brings up a really good point. If you look at it this way, well, so the next thing is that the wedge product, right? So I can take two elements of the algebra. The multiplication element is this. Now, very rarely do we actually go this deep into understanding the exterior algebra. I'm kind of doing this because I feel that this was really helpful in understanding what they meant by an exterior algebra, is to literally construct the thing or deconstruct the thing to understand what it means to be a member of the algebra. You have to be able to add two elements together. Well, this is how you do it. You need to be able to multiply two elements together. Well, multiplication is with this. So what's going on there? So if I have A, B, C, dot, 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 D, wedge, E, F, G, dot, 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 H, like that. I need to be able to do that wedge product. So what is actually happening here? And this leads to a really interesting idea that when you really go dig into this, you start, I think it provides a lot of clarity. But before we explain this, let me explain something else, because I think it'll help illuminate how this wedge product works in the exterior algebra. And that is, imagine we did this. Imagine we took 0, A, 0, 0, all the way to 0, and we added it to 0, 0, B, 0, 0, like that. And the result, of course, is 0, A, B, 0, 0, like that, right? Because it's really A plus 0, which is A, and it's B plus 0, which is B. So you can actually do this addition without any trouble using the vector addition property of the exterior algebra. That's what this is. This is the vector addition of the exterior algebra, which is a vector space with this monoid product. But what's interesting is you can actually think of this in the very unusual way of A plus B. And I'll put plus in quotes because it kind of is A plus B, isn't it? I mean, this is the sum of these two. And these two, the first one only contains A, no, it only contains B. So I found a kind of a way to add A and B together in this exterior algebra. Now, you can never add A and B together there's no sum, because remember, A is an element of one vector space, and B is an element of a totally different vector space. There's no way to add these things together. There's no defined addition property. But when you consider things in terms of the exterior algebra, all of a sudden there is an addition property where you can kind of think of A plus B as being added together. You always have to remember it ultimately in this context here. You have to understand it in terms of these n-tuples. But this is exactly how you would add polynomials. Remember, x squared plus x cubed plus x to the fourth. You can't really add those together. But you could create polynomial addition in exactly the same way as you create this sort of addition. And in fact, polynomial addition has the exact same structure as this, and it's also a graded algebra because you can multiply polynomials the same way. I mean, you can multiply polynomials just as you can wedge together these guys. Now, polynomials go on forever, right? They don't have... it's not exactly the same. They don't have an upper limit. You can have unlimited powers. So x to the fourth plus times x to the 16th is x to the 20th, no problem. You just stick it in there. But in this case, there is a problem because nothing after the nth exterior power can exist. But now if you think of this in terms of, if you think of addition, this addition being a representative of the exterior algebra addition, now you can understand this idea in terms of linearity. And the way it would work is like this. You would say, let's just do A, B, C, wedge, D, E, F, like that. And now we'll also assume that the dimension of the underlying space is only 2. I just want to keep this kind of small, right? D, E, F. We're taking two members of the exterior algebra. That's this guy and this guy. They're both elements of the exterior algebra. This is the monoid, so you need to be able to multiply these two together. This is the monoid multiplication. So we need to know how to do this. So we want to think everything here is linear. And so in order to think linearly, we're going to replace these guys with this weird sum interpretation. A plus B plus C wedge D plus E plus F. Where now these sums here are to be understood. Let me get rid of this, this page. They're to be understood in this context, right? They're to be understood as this kind of sum. So when I say A plus B, I'm actually talking about this large tuple plus this other large tuple, and the result is this other large tuple, right? I'm not actually talking about something like this, where I'm literally adding A and B, because this addition symbol doesn't really exist except in the context of the exterior algebra. So whenever you see two different forms added together, and remember, these are two different forms, right? This here is a zero form. That, well, not a zero form, a zero vector. We're doing this in the Pvector spaces, right? So that's a zero vector, that's a one vector, and this is a two vector. right? And there are no 3 vectors because the dimension of the underlying space is 2. Likewise, 1 vector, 2 vector, 3 vector, and that's how these 2 tuples are organized. Actually, I said dimension v tuple. It's actually a dimension v plus 1 tuple, right? Because you've got the 0 in there. Okay, so now if I convert this, because I want to study the wedge product of 2 arbitrary elements of the algebra, I think of it in terms of this, and then immediately I can say, okay, a wedge d plus a wedge e plus a wedge f plus b wedge d plus b wedge e plus b wedge f plus c wedge d plus c wedge e plus c wedge f. Right, and then I start looking at it. And then I start looking more carefully. This is a 0 form times a 1 form, so that's a 1 form. This is a 0 form times a 2 form, so that is a 2 form. I'm sorry. This is a 0 form times a 0 form. This is a 0 form wedged with a 0 form, so it's a 0 form. This is a 0 form wedged with a 1 form, so that's a 1 form. A 0 form wedged with a 2 form, that's a 2 form. This is a 1 form wedged with a 0 form, so that's a 1 form. A 1 form wedged with a 1 form, that's a 2 form. 1 form and a 2 form, that's a 3 form. This is a 2 form and a 0 form, so that's a 2 form. That's a 3 form, and that is a 4 form. So I know right away that that's going to be 0, that's going to be 0, and that's going to be 0. And then the result is going to be, I'll put the result in blue, a wedge d. Remember, a wedge d is the same as a times d. The wedge product becomes regular multiplication when you're dealing with 2 0 forms. Or whenever you have a 0 form, the wedge product, a wedge anything equals a times anything, right? It doesn't change the it doesn't change the it doesn't change the rank, I guess, of the tensor or of the form. So anyway, so this is a wedge d. Is that the only 0 form here? Yeah, I guess that would be the only 0 form. Then the 1 form is a wedge e plus b wedge d plus. I guess that's it. Now in this case, this plus is in fact the addition property of the first exterior power, which is just the addition property of the vector space V, right? Because this is basically going to be a constant A times a vector E plus a constant B, plus a constant D times a vector B, like that. So that one actually is, but that's the rule, right? That's the rule of how you add these things all together in a created algebra. And then the 2 forms is A F plus B wedge E plus C wedge D, right? Those are the 2 forms. And then all the other ones are 0, or if you prefer, we just cut it off. So that is how you understand a wedge product in the exterior algebra. It looks like these tuples, but we reinterpret these tuples with plus signs so we're more comfortable with the linearity. You don't need to do that. You could just say, oh no, it's just linear by slot. And you can just say A, D. You can say this first slot is going to, and then you just figure out the forms. The first slot is A times D. That's going to be the only 0 form. The second slot will be of all the 1 forms, so that's A times E plus B times D. Okay, you figured that out. And then C will be all the 2 forms, which is C times D, B times E, and when I say times, I mean wedge, and C times D, B times E. Was there any others? A times F, right? A times F. So that's a little bit more of a thorough dive into how the exterior algebra works. On review of my previous lecture, I don't think I didn't highlight this principle. But don't ever be confused. If you ever see the addition of 2 forms or any 2 vectors that are not in the same vector space, then something like this must be going on. Something like where's my algebra? Some form of the algebra. You must have created some kind of graded algebra. Okay, so what next? So, all right, I think I'm just going to make this a bit of a recap lecture because there were some flaws in my previous lecture about p-forms. Not factual flaws, but presentation flaws. So let's consider the dimension of a vector space with dimension 3. So for p equals 0, the basis of ultimately the 0th exterior power, the p vectors, right? The p vector space, or the p form space. The p form space will look like this. The basis is simply the number 1, right? When p equals 1, the basis for the p vector space is going to be E1, E2, and E3, or if we're using the coordinate basis, dx0, dx1, dx2. If you're using dimension 3, you're probably hanging out with a lot more engineering math, and it's much more likely that you'll write a dx1, dx2, dx3, or even dx, dy, dz, something like that. But that would be the basis, and it would, oops, whoa. Well, anyway, so that would be the basis for this, except I need to do something. This is actually not the basis for, this is the basis for the p form space, right? For the p vector space, it's going to be del 1, del 2, and del 3, or del 0, del 1, del 2, depending on how you want to count. So that's the basis for the p1 space. And this, the p form space here is lambda 1 of v, like that. If the second, for p, the second exterior power space, the basis vectors are going to be E0 wedge E1, E0 wedge E2, and E1 wedge E2, like that. Those will be 3 basis vectors. Its dimensionality is 3. Here the dimensionality is 1. Here the dimensionality is 3. Here again the dimensionality is 3. And that makes sense because we know that the dimensionality of P, equals the dimensionality of n minus p. In this case, it's 2 and n minus 2 is 1, right? So those two dimensions have to be the same, and they are. And then the last p form has a dimensionality of 1, which also follows this rule, and it has a single basis vector, which would be E0 wedge E1 wedge E2. Now, in the coordinate basis, this would be del 0 wedge del 1, del 0 wedge del 2, del 0, I keep saying del, but I mean partial 0, partial 1 wedge partial 2. And here it would be partial 0 wedge partial 1 wedge partial 2. And in the p form space, which is this, right? In the p form space, it's dx0 wedge dx1 wedge dx2. In the abstract form, it'd be E0 wedge E1 wedge E2. Where by abstract I mean if I put in E for my basis vectors, whatever they are, where of course here I always mean the coordinate basis, which is derived from the fact that it's on a manifold with charts and all of those facts that we discussed in the What is a Manifold lecture. And this is only one-dimensional, right, which of course is the same as 0, so which makes perfect sense according to this rule that we already did. So that's the way it is for dimension v equals 3. Now if we add a dimension and we turn this into 4, right, It's not quite as easy as just turning it into 4, but we could try. We could say, well, the p equals 0 still has one dimension. That's always going to be the case, regardless of the dimensionality of the underlying vector space. This one is going to get an additional vector, which means these guys get additional vectors, right? This, again, the only difference here is between how you count. This, let me erase here. We've already seen that, right? Just erase it. So this part here, we got E0, E1, E0, E2, so now I need to go E0, wedge, E3. I need to add that. And I got E1, E2, then I need E1, wedge, E3. And then I think I need E2, wedge, E3. So we have 6 dimensions here for the p equals 2 space. And and again, all right. So these all have to be down below, right? This is the p vector space. The p vector space. I'm so used to using forms that I'm screwing this up, right? This needs to be the p vector space. 0, 3, 1, 3, 2, 3, right? So it's like that. Those belong over here, right? E0, wedge, E1, E0, wedge, E2, etc., all the way to E2, wedge, E3. And there's 6 of them. So those are the 6 there. So now with 4 dimensions, the 3 form, or the 3 vector space, is going to have E0, wedge, E1, wedge, E2, E0, wedge, E1, wedge, E3, E0, wedge, E2, wedge, E3, which is 1, 2, and then it's E1, wedge, E2, wedge, E3. So there's 4 of them here, which exactly matches 4 here, which makes perfect sense because of the rule that the n minus pth space has the same dimensionality as the pth space. And then finally, I get an additional vector space once I boost the dimensionality v up to 4, and now I get this, but it always has only one dimension, and it'll be, excuse me, it'll be E0, wedge, E1, wedge, E2, wedge, E3. And likewise, all of this likewise exists over here. So that's yet another piece of review about the basis vectors. And then the other thing to remember is that an arbitrary, let's get out of red, an arbitrary member, let's say Q, if Q is an element of the pth exterior power, well, now I'm talking about p vectors, and I'm just talking about p vectors just because we haven't used them before, but this is the same logic as it would be for p forms. I could just as well write Q, well, p forms are different objects, but understand that the math is going to be the same. So if Q is an element of the pth exterior power, I can write Q down. If this is sort of Q stands for the actual tensor itself. Remember, all these guys are tensors, right? They're all members of the zero. In this case, the p0th tensor product space, right? It's a subset. But I can write Q in component form as Q with strict basis, alpha, beta, indices, alpha, beta, ... say delta, where there are p indices, and then it's dx alpha wedge dx beta ... dx delta, where there are p of these, and these little lines mean that alpha is less than beta, less than delta, and that is called strict components. Those are strict components. If I don't do that, if I don't use strict components, then I really need to add this factorial, 1 over p factorial, q alpha beta delta dx alpha wedge dx delta. And what happens here is this factorial, we know that this is antisymmetric. That's how this whole thing is built, right? So now that I'm summing over all possible alpha, betas, and deltas, here I'm not summing over all possible ones. I'm only summing over the sequence where alpha is less than beta, which means I'm never going to get, during this sum, if I keep to this rule, I'm never going to get two permutations of the same collection of basis vectors. Here I'm summing every permutation, so I'm going to get every possible permutation of these is going to show up, and they only differ by a sign. But every time a different permutation shows up, if the sign switches, the sign here will switch too, because this is antisymmetric in all of its indices. So what ends up happening is I end up adding this up p factorial times, because I hit every permutation. So I have to divide, so I multiply, so I have to divide essentially this coefficient by p factorial in order to make it normalize correctly. But that's fine. We can do that. That's an acceptable way. The actual component is this thing, right? This is just this antisymmetric. Well, the actual. So what's going on here is, it's hard to say what's the component and what isn't. And the reason it's hard is because for every permutation here, it's the same basis vector. It's simply a constant times, so let me put dx beta here. Say I also had this component, dx beta, dx alpha, dot, 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 dx delta, where the only difference is this interchange. Well, that interchange introduces a sign, right, a -1. But that's linearly dependent, right? So these two are being linearly dependent. That's not really a different basis vector. But if I were to treat every component here as independent, then this would be, or every permutation as, I'm not treating it as independent, but I'm treating it separately, then this is the component of that sort of separate treatment. But that's not really the component in a basis, because a basis is supposed to only have the minimum number of basis vectors needed. You know, if this is a dimension 4 vector space, but I decide to create a basis of 10 basis vectors, that's kind of a waste of energy. So there is this, in this case, the wasted energy makes things a little bit simpler because you get to exploit the summation convention. But if you want to exploit that convention, you got to multiply by 1 over p factorial, or else you're going to overcount. Anyway, so there's these two ways of writing this down. There is actually a third way of writing it down. Q could also be Q alpha beta delta dx alpha tensor product dx beta tensor product dx delta. You could do that and just insist that this guy's totally antisymmetric. And then you've basically got the longest way of writing this out, right? Because now you are expressing everything in the basis of the tensor product space, but because it's antisymmetric, you know it lies in a subspace of lower dimension, So this is even less efficient. But the one that nails it, in the sense that there's one component for every independent basis vector, is the strict components. And we'll talk a little bit more about that in the next lecture, because we're going to talk about the transformation of the strict components. And that transformation property is not the usual tensor transformation property. And it shouldn't be, because the usual tensor transformation property applies to this guy. This guy will always transform like a normal tensor, like we learned about many lectures ago. This guy will not, which is interesting because it's really the same guy, right? It's just how you're writing it down. But when you enter that subspace and you change the system of how you actually write the thing down, well, you change the transformation rule. And that's what's the introduction of what we call tensor densities. And we'll talk about that in the next lecture too.